I'm going to get into lines and planes really quickly here, but just a couple of quick things I want to point out when we talked about dot product or the inner product and the cross product or the outer product. The result of a dot product is a scalar, just a number. Result of a cross product is a vector, a whole vector. This. I really wanted my students to get at least that much straight. If you cross two vectors and get a scalar, you did it totally wrong. If you dotted two vectors and got a vector, you did that totally wrong. I had some students in some other calculations would just write A, B with no operator between them. That doesn't make any sense. There's two ways to multiply vectors, dot product and cross product. They're not the same. AB doesn't have any meaning. You're either dotting them or crossing them. Anyway, so let me get on to lines and planes and first lines. So we've got our three-dimensional space, X, Y, and Z. We wanted to describe a line in that three-dimensional space. Let's say we're given 2 points on the line, P1 and P2. And then P over here without a subscript indicates just any other point on that same line. Well, first I can describe the points as position vectors, So R1 is position vector to this point. R2 is the position vector to that point. So that vector R2 minus R1 would give you this little vector A, which has a magnitude and a direction. So any other point on that line, I could describe it with a position vector R without a subscript. And how would it be? This, say R minus R2, would be that guy. That guy, this little vector from P sub 2, oops. This little vector from P sub 2 to P is R minus R2. And they are parallel. This vector is parallel to that vector, which means one is a scalar multiple of the other. So I can say R minus R sub 2 here equal to some scalar multiple of R2 minus R1. Rewrite that a little bit. And I could say R, the position vector to any point on the line, equals R2 plus some parameter T times A, where A is this difference. I could have used R1 as another reference. You know, I could say P is R1. I could say I could have used R1 instead of R2. So R minus R1 is also parallel to R2 minus R1. Here I'm using a different parameter, but you see they're both the same format. I have an R, the position vector to the point is some given vector, position vector to a given point on the line, plus a parameter times A, where A is parallel vector there, which you get by differencing any two position vectors on there. Sorry I didn't explain that super well, but that's how we parameterize the line. These parameters, T or S, usually we're using T, would be a number that goes from minus infinity to infinity. And that gives you all the points along the line. So what you need really is a point or a position vector to a point on the line and a vector that it's parallel to. Those are the two things you need to write to parameterize a line, to write the equation of a line. And you could get that position vector from 2 points along the line just by differencing their position vectors. I could write other forms of that. If I say R, break it down into components, X, Y, and Z components. Remember, these R now are position vectors, not just free floating vectors. These R's have their tails at the origin. A is just a direction vector. This A would not have to have its tail at the origin. But if I broke it down into components, this is R, say this is an R sub 0, which is a point we know along the line. And we have a vector that's parallel to the line. Break it down into its component parts. That means would mean then X equals X0 plus T times A1. Y would be Y0 plus T times A2. I have a different way to write the line by using 3 separate equations in each direction. This is called the parametric form of a line. If you look here, you could solve for T for each of these. So T here would be X minus X0 over A1. A1 isn't 0. If I do that, I would get these 3 equations, or these 3 things being equal to each other, as long as those A's aren't 0. If any one of the A's is 0, I would write it this way. I would say A2 is 0. I would same 2 for the other 2 guys, the X part and the Z part. But because A2 is 0, I would just say Y equals Y0. So this is a little nuanced part that you have one of them equal to 0. This format for writing either of these, this format here for writing equations of lines, or equation of a line, is called the symmetric form. We have 3 ways of writing them. It summarizes 3 ways: the vector equation, parametric form, and the symmetric form, where these R's mean position vectors. Position vectors, their tails are attached at the origin. A is free floating. So here's an example to get all 3. Write the parametric, write all 3 forms actually. For the line that is parallel, for the line through this point, and parallel to this given vector. Well, we have the R1 that we need, point on the line, 1, 8, minus 2. Here it's expressed as a position vector. And the direction vector, minus 7, minus 8, 0. So we have the 2 things we need to write it in any of the forms. For the parametric form, for X, I'll have 1 minus 7t, whatever my parameter is. For Y, it'll be 8 minus 8t. For Z, it'll be minus 2 minus 0 plus 0t. So this right here is the parametric form of the equation of the line of this line. Let's see the symmetric form. Well, I've got a 0 for Z, so it's just going to be Z equals minus 2. And then the others are going to be X minus 1 divided by minus 7 equals Y minus 8 divided by minus 8. I could have multiplied both of these by minus 1 and got plus 7 down here to plus 8. These 2 guys are equal, and Z must equal This right here is the symmetric form. In the vector form, r equals r sub 0, which is the position vector to this point, plus t times this vector, -7, -8. There it is, all summarized. The only nuance is this symmetric form when one of the three components is 0. If two of the components is 0, of the direction vector is 0, you wouldn't use the symmetric form. It doesn't make sense. Right, after that, we'll do planes. That'll be it for the vector intro.